So we're this is the Mosul Observatory for a little over 50 years. We've been studying the atmosphere of the sun, trying to understand how energy transfers sort of from the sun into the atmosphere. I work for the National Center for Atmospheric Research, so we mostly care about how the atmosphere heats and stuff. But this site's just basically dedicated to somehow studying solar processes. And for 30 plus years we've been running coronagraphs to take pictures of the solar corona and try to look for things like coronal mass ejections and stuff. So this is what the corona of the sun looked like today. So if we had a solar eclipse somewhere in the world today, you could go stand there, you would see this, but you wouldn't see these weird lines because my camera does that, and this was some dust I should have cleaned, that's a piece of dust. But this part here with the arms, that's actually magnetic fields out of the sun and mapping where the solar wind is. So this phenomenon, there's some particle, an electron, outside the sun following solar wind. A photon comes out, hits it, scatters down here, and we collect it. This stuff is about 1 million times dimmer than the disk and quite a bit dimmer than the blue sky. So it's really hard to measure this anywhere you get any scattering particles. So as soon as that cirrus comes by, we do something else. Okay. As soon as something happens, we do something else. We're in the process of building or upgrading an instrument to look at a much closer region of the sun right in here and map all the magnetic fields. That was running until December when we shipped it back to Boulder to get new instrument, to get new cameras. So when I'm not observing today, I was writing software for the new cameras. So the cool thing is, by doing this, we can actually map or watch these eruptions happen. We have some spacecraft that do similar measurements, but they're a little bit more conservative with their occulting disks, so they're going to sort of not look real close in the visual because they don't want to burn their instrument up. Where we, you know, if I burn my camera up, I get fired, but there's another camera on the shelf. With the spacecraft, you're dead. I mean, it's over. So here you can see 3 different eruptions that happened during 2015. We're in the solar minimum, so we didn't get much of anything for the last 2 years. But these are cool. You can see there's a helicity. They spin as they come out. There's multiple bow shocks in there, shock waves going through.
So what type of images?
So these are green. They're 730 something nanometers. So if you could go outside with green sunglasses on and just get a solar eclipse that lasted, this is a 3-hour video, so a 3-hour long solar eclipse, you would see that. This is something that your eye could see, except because of all the scattering properties of the atmosphere and that big bright thing under there, under that little aluminum disc, we can't do it with our eyes, right? But this is a white light corona, so it's going to be the same, essentially the same in most of the visible range. Turns out green was good for our instruments and for the way we do some of the polarization tuning. But
where in the optical path is that aluminum disc?
So lens, disc, instruments.
Okay.
So we have uncoated singlets, very narrow wavelength.
Really?
We don't really care. So we have a big magnifying glass pointing at a little aluminum mirror that the magnifying glass isn't so big we burn up our aluminum mirror, and it's mounted, it's glued into a little field lens piece of glass, so everything else goes past it. That spot there with some dust on the field lens.
So how big is the singlet?
20 centimeters.
20 centimeters.
You know what? Let's go see it. Any more questions about this?
Yeah, I do. I've got a couple.
Yep, sure.
One of the main questions is that the corona is about 1 million degrees.
Yeah.
Okay, and so as you go lower, the chromosphere is only about 100,000.
Yeah.
And the photosphere is about 5,800.
Yeah.
So one of the big questions is, why is the corona so hot? Does that have to do with magnetic fields?
So that, there's this process of alpine waves that explains a good chunk of it. So there's a mechanical pressure wave process that happens preferentially near the poles. It actually puts more energy up into the corona. Doesn't account for all of it. We still don't know.
Okay.
But, so our magnetic field imager is one of the things where we added better cameras to try and go probe that.
Okay.
We were first to see those alpine waves actually doing those mechanically, like putting energy up there that's more than you'd expect from just the pure photoradiation. off the chronosphere.
Also, you know, the corona, is you find the shape of the corona correlating with the solar minimum, for example?
Yeah, so it tends to, near solar max, be more symmetrical sort of everywhere, and then towards the minimum, come down to the equatorial plane.
Yeah, yeah. Okay.
So, I don't know if I guess I'm making some assumptions here, but this thing here is actually an eruption of charged particles. So the reason why we sort of might care about this, these aren't pointed at the Earth, but if it was, this is a bunch of energy coming. So if you're a satellite or an astronaut, you might not want to get hit by a bunch of electricity, but it also comes and does the northern southern lights and charges up things like power lines and stuff. So understanding how these happen are good for spacecraft owners and also people who do things near the poles. Yep.
Is watching the corona like this the way they map out and try to predict rotating regions?
No, so some of that's done with spacecraft. And you're able to do that with the UV mostly. The UV doesn't quite get you some of the particle fluxes right, but it's easier to see those coronal holes and things.
They observe sunspots too.
Yeah. So this image right here actually came off that GONG, that helioseismology thing. The Air Force threw in a H-alpha filter. So if you ever go look at a little telescope that's red, you're seeing the sun in H-alpha. So you can see this today. But there's a little sunspot right there, and some flashes and stuff. And some clouds. This is today.
But it's not live right now.
Yeah.
It's not live.
Earlier today?
Yeah. So it might go all the way to yesterday, but it's a loop of the last little bit.
Did you put all these pretty videos up for us?
So this right here was a website I made. We threw together some stuff just to show people, but this we look at continuously while we're running the instrument, and I would be looking at more weather webcams if I was up here at Loon.
So the scope Alpes Mountain.
It's equatorial. Yeah, so this is what I would see if I was.
There's going to be clear weather.
Yeah, I mean, if you see, the clouds coming in, acting angry, every once in a while it's good enough. There's cars here. Get a little bit of Mauna Loa, and actually watch how our instruments move over the course of the day, and a little bit of weather information. Sometimes it's predicted to know when the human.
All of this is videotaped on the cloud.
So our webcams record every twice a minute or something. Our instrument isn't recording data right now. That's why. But the guider is recording its voltages. Also, why?
Use monitor seeing also.
We do some seeing monitoring, but it's not directly applicable. So we fake a number in arc seconds, and it's not quite right. It's more of a CNN profile, and it's a scintillation, and it's a thing you would do with the sun and not any other way. But I don't know what it's closest to. It's not quite a DIMS or anything.